Hello, and thank you very much for the introduction and for cueing my first remark. Oh, by the way, I don't know anything about 50 years. When I went to IBM, it was 49 years ago, and I presume that what happened before the Big Bang, as far as I know, is unknowable. Now, I know you're probably wondering if I'm going to start with the same joke as before. Can you hear me okay in the back? Okay. I gave a talk a few years ago, and I was some 15 minutes into the talk before I thought to ask that question. And when it was evident that the people in the back couldn't hear, about 3 rows in the front got up as one and moved to the back. So it's better to ask at the beginning. Okay, let me start by, for continuity, reviewing a slide or two from 2 years ago. Just to introduce myself, my background, well, I started APL, as I said, 49 years ago, and eventually had some peregrinations. Before that, I guess my true spirit is mathematical. And the reason I show up here and try to make friends is because I'm trying to learn how to do Windows programming instead of the DOS stuff that I'd been surviving with for 30 years. I've made some progress, by the way. I'm coming along. And maybe it may even be that Dyalog is my platform of choice now. Maybe I'm, if not as comfortable there as in DOS, the advantages somewhat make up for it. And now Morton approached me a few years ago and, politely asked if I minded being done a favor and would object to his generosity at helping me with Dyalog, and I don't mind at all. And of course, one thing that I was just attracted by the toys of Dyalog. Some of these things I knew vaguely about that are very clever. And so to start off, I'll mention my first defined operator. Eventually, I got to a place where I actually had a need to use this. So I'll try to show it. Let's make sure we have enough screen here. How's that? Bond. I know how, yeah, I can do it. See what you do is you click over here. Okay, now I have to remember the keystroke. It's Alt-N. Should I do that now or should I just enter now? I'm not sure. Okay. Any other bright ideas? Okay. Now can I Alt-N? Alt-N? Okay. Yeah. Okay, so a problem that occurs in my program, so to speak, is a DNA application, which I'll talk a little bit more about, but all we have to know for the moment is that it involves mixtures. And what is a mixture? A mixture means a situation where you have the DNA of one or more people. The biologists or the forensic people, they all say 2 or more, but as mathematicians, we know that that's an arbitrary constraint. And in fact, you gain by thinking of it as a 1 or more. I'm working on 0 or more. I keep pressing. Sorry, I'll get the hang of it. It's only been about 40, 50 years. If you hit only Alt, then you'll select a menu. You must be more decisive. Thank you. Okay, so let's suppose that I have a handful of small probabilities which I wish to average. Or maybe that's not, let's see what's going on. The point is, because they're small, I store them as logarithms. I store the logarithms of probabilities. And then I want to take an average But if you take the average of the logarithms, you're nowhere. Well, you're somewhere, but not where I want to be. So, anyway, I feel I'm soon going to need, oh, I haven't hit enter yet, I see. Okay, so I'm actually storing those numbers, negative 100 and so on, and I'm going to define an average function. And so essentially, so it turns out that if you convert the log probabilities to probabilities, and then take the average, you end up with this number here, and if you compare it with the numbers you started with, you get some sort of intuition about how average of those exponential notation things works out. If I gave you a whole 20 seconds, you could work it out explicitly. But then I want to store things as logarithms, so then I have to do this operation. So Bob is perking up because he talked about this morning. Internally. We move to the probability domain. And we average, and then we move back. That's the recap. Okay, now why do I do this? Because my probabilities are sometimes really small. If you have a picture, a pretty close analogy is, if you take a picture with a digital camera of a person, you'll get a certain set of pixels. And if you re-photograph the same person with the same camera in the same position again, you may get the exact same set of pixels, but the chance will be a rather small number. But on the other hand, it's an enormous number compared to the chance you get that set of pixels from a different person. And that's indeed what I'll be doing with DNA. Okay, so I have these really tiny numbers, and if I take a look at what I've done, it doesn't work at all. I lost the numbers altogether, so that's why I absolutely need these logarithms. So now I just set them up as logarithms, and I'll choose these. Oh, I see it. Okay, it turns out that I end up with these three logarithms. And then I average them, and it doesn't work. So it's not quite that easy. It doesn't work because after you average them, you get 0, and then when you try to move back into the log domain, you can't. And it's just as well, because once you got 0, you'd lost your information anyway. So the trick is that you offset the logs. Let's take the largest of the logs and offset, so we get these nice comfortable numbers. And then we'll take the 10 log of that, we'll convert to probabilities. Now we lost all of our significance on the smallest probability, but that's okay. It's so small it deserved to disappear, because it's much smaller compared to the others. Now we average, and now we can convert back. So this whole business reminded me of something, and convert back. Then we have to undo the offset business as well, of course. So that's the storage version of the number I want. So that's what I did. I toyed with whether to say open drawer, close drawer, and I decided to say translate, untranslate. Which I recall being called conjugate from algebra. So therefore, gave me the chance to write this function. No, it's not called a function, it's called an operator. And let's see, why are we doing that? Don't know. Okay, now to convert logarithms to probabilities, we have to subtract the offset, and then we have to take the 10 exponent. And I discovered that you have to write it this way. You have to bind all the functions. Why do you have to do that? Well, for example, I couldn't do it with a defun. Yeah, but I mean, I like your answer, and it'll give me some insight when I think about it.
Why not? Couldn't you do it with a defun?
Because of this. Because it has to be something I can invert. And the inversion, I still haven't figured out all the... I'm sure that I'm going to learn something from the audience after I finish this. Because here's the problem. I had to calculate this number and then do this. Because in this function, what you have here isn't a symbolic reference, you have a number. But now you can invert it. This isn't very readable to me, but some of the system types in the audience will read it with the same fluency with which I read Spanish, let's say. So it works pretty well. And as I recall, it's essentially, for my purpose of my application, it's as fast as doing things step by step, and I like very much the readability, so I was delighted with that. And that's automatic. I didn't have to program that. Okay. Okay, DNA has these interesting properties. The most amazing, perhaps for our purposes, is that it's digital. So that means that we can deal, it's comfortable, it provides opportunities to use mathematics for that reason. And nice mathematics, combinatorics, for example, not just sleazy numerical analysis. Individualizing, meaning it varies from person to person, and genetic, which won't matter today, but that does mean you can identify fathers and you can go on Maury Povich and make all sorts of money. Of course, at the cost of your soul. Now, here's a little more about DNA. Here's a DNA profile of a person, and this comes out of a machine that costs a lot of money, but the result is something very understandable. We have a set of things called loci, which is Latin for locations, and the code is D8 means that it's on D chromosome number 8, and D21 is on chromosome 21, and so on. In D8, well, let's say take a look at D7. The commonly occurring sizes in the population are sizes 7 through 13, and 10 is the most common among Caucasians. And this particular person has an 8 and an 11, and the reason they have 2 is because they had 2 parents, this particular person, each of whom gave them one of the things. It could have happened that they got the same thing from both parents, but it didn't happen. And if you have a mixture, in this case is more than one person, then you're likely to get more than 2 spikes per locus. And oh, by the way, the height is a measure of fluorescence. And the fluorescence comes about because you have you start out with a small number of cells of DNA at the crime scene. A small number like 50, let's say. And then you go through some complicated processes, which are mainly chemical, but also involve pipetting. And they involve amplifying these things for several reasons. One is to isolate the particular fragment of interest. Another is to make about 1 billion copies so that it's enough to detect. And a third is to attach a fluorescence to each molecule so that you can detect it. And so what you see here, the amount of fluorescence, is an indirect measurement of the amount of DNA you started with. It's very approximate, but it's indicative. And we need to model the error in it, in fact. Okay, let's suppose we have what they call a direct match, which means that we have at the crime scene a profile that looks like, well, is only one person. And we have a suspect. And we want to say how strong is the evidence that this suspect is in fact the guy we're looking for. So it turns out, if you think through the logic, what you're interested in is how likely is that picture, if it is indeed from this guy, compared to how likely it is from a random guy. And so that picture is analogous to my photograph. I know they don't look the same, but they're quite similar. So the probability of seeing that exact from an 8 and 11 man, from if this guy is the donor, is 1. The probability of seeing that picture from a random man depends on how common 8 and 11 are, but if you work it through, it's about 1 in 20. So that means you divide the first number by the second, and you put the name likelihood ratio on the ratio of those two likelihoods, and the likelihood ratio is 20, which is moderate evidence that this is the contributor. Then you look at the next locus, and you do the same calculation, and you multiply, because the genetic information is independent between loci because of the way that procreation happens, that chromosomes assort independently. Mendel said so. So the accumulative likelihood ratio is simply the product of the per locus likelihood ratios. I'm up to the hundreds already, and if you'll let me go for 15 loci, I'll be astronomical. So we can confidently cut off this guy's tongue or whatever the punishment is. Now I want to look at it in a slightly more sophisticated way. So I'm going to call this advanced undergraduate forensics. And because now I want to take into account the height. I ignored it a moment ago. I ignored that part of the evidence. All right, so now when I talk about the EPG, I'm no longer talking about 811, I'm talking about 811 plus those heights. Now what's the chance that this guy would give me that exact EPG down to the pixel, down to the height? It's certainly much smaller by this factor, which I won't try to evaluate. And how about on the other hand, what do I get for the other guy? Well, I still get the 1/20th times the same factor. Whew, that's lucky. Okay, so it turns out I don't need to evaluate the factor because it cancels. So this will extend to multiple loci as before. On the one hand, because the genetic information is still independent between loci. Secondly, the quantity information is not independent between loci. The DNA quantity is dependent across loci, but that's not going to matter because of the fact that it just canceled. However, let's look at a tougher problem. Let's look at a more than one person mixture. Now, the heights vary for the reasons I mentioned a moment ago. In the first place, if one person contributes more cells than the other, they'll tend to contribute higher peaks. Secondly, there's this stochastic randomness from the replication process, and I think also from pipetting. And also, there's some really unpleasant, messy things that luckily we don't have to consider. So the consequences are that the peak heights are correlated both between and within loci when you consider the same person. The correlation is imperfect, and let's see, why did I put in dropout here? I certainly don't want to go that far I won't have to worry about that. So when we have several loci, we're interested in the heights. And, okay, we're now legitimately in graduate area. So I'll speed up. So now the probability, I don't care. I'm not going to worry about. So I'm going to consider two hypotheses. One hypothesis is that the mixture is the guy and somebody else, I've no idea. He took off to Honduras before we could test him. And the other one is that it's two guys who disappeared. That's what the defense is going to complain. He's going to say, no, guy is innocent. It's just coincidence that he seems to match. Look, so we'll test and see how big a coincidence they're trying to claim. We should ignore. Two unknowns. Now the unknowns, there are a great number of combinations we can imagine for the unknowns, and I've laid out a few of them. In the case of D11, the first person could be 1111, in which case he's quite a minute contributor, and the other guy could be 812, or these things and a whole lot of others that I didn't feel like listing. And at the same time, for D8, we have a lot of combinations. Now, the first one that I listed is the most reasonable fit for those first two loci. As I said, it looks like this says that the yellow guy is a rather small contributor because each of his peaks is half of what you see for 11, whereas this guy, the 8 and the 12, are rather larger. This guy's contributing well over 2/3 of the total fluorescence, and this guy, well under 1/3. And at this locus, the 1315, well, it's a little tricky what is going on. If this guy's contributing 1315, and this guy's contributing 1316, that means the 13 is divvied up between two people. It is additive the way these things work. So what this guy's 1315, based on the 15, which is tiny, it must be that he's contributing a tiny proportion of the 13, whereas the rest of the 13, which lines up with the 16, so this is again, wait a minute. Oh, this is again a minor contributor. Whereas this one, the 1316, is obviously the big 16 and the majority of the 13. This hypothesis, so I put 100% here, meaning that it's a relatively good fit to the data. This hypothesis here is a rather bad fit because at D8, Mr. Green has inconsistent contributions. He's the only one contributing to 13 to 15, so based on this hypothesis, it's a very unbalanced contribution, a lot of 13 and a tiny bit of 15. Let me see if I've animated some of this stuff. Yeah, I got pictures. Okay. So, nonetheless, that's something I can cope with. I can make the evaluation without difficulty of a situation like that and come up with a number like this. This one here is difficulty of a somewhat more troublesome sort because it's interlocus, and we'll see in it, and you may anticipate why interlocus is a problem. So in this case, the guy is clearly, that is Mr. Yellow, is clearly a major contributor to D7 and a tiny contributor to D8. That would be quite unusual. That would require a remarkable stochastic accident. That is D7 alleles amplified well and his D8 alleles amplified horribly badly. Now, if we only had 2 alleles ever in the world, I could work that out. But we have a lot of alleles, and we have a huge number of genotype combinations here. At each locus, we have, let's say it's 100 at a locus. I mean, with only this small set of alleles, maybe it's less. Maybe you want to think 20 combinations. And at the next locus, it's not 20 corresponding. I mean, you have to take an outer product. So if there are 20 ways to line things up at this locus and 20 at this one, then that's 400 for 2 loci, and a really, really big number for 15 loci. That's the problem. So it's seemingly, oh, okay, I'll time it. We'll leave out the stories. The net is that unless you can find a way to do this locus by locus, you have 10 to the 30 or so combinations to be concerned with. So the model program would be something like this. And you just don't, I mean, for the most crimes, you just don't have that kind of time. If the question is, did the Jews kill Jesus? Okay, I can wait. But seemingly it can't be done. This is well known in the business, and consequently the other people who had written programs of this sort use Markov chain Monte Carlo. And I think they're proud that they understand it a little bit. I think they only can understand it a little bit. I think it's a very complicated thing, and I'm scared to death of it. Here, by the way, just because it's a really nice picture, is what the probability, the likelihood looks like as a function of the proportions. So what I net, and net what I need to do is integrate under this surface. What I'm showing you, of course, is log probability, because as I explained at the beginning, I like it. If you look at it in terms of probability, that is a really sharp spike. So there's virtually no contribution more than about 3 or 4% away from the maximum likelihood contribution. So it's beneficial to pile things in the right order. The time is the obvious one. Avoiding MC is a great one, because now I actually understand what I'm doing, which is important to me. And also, it's a subtle point, thank you, but you can calculate the prosecution and defense hypotheses independently, which means that unlike everybody else, I can take into account the possibility. It sounds weird at the beginning, but the best hypothesis for prosecution and defense involve differing numbers of contributors. It's important because that happens a good percentage of the time, and it's possible because contributor isn't really a well-defined term. It's a relative term. So it changes depending on the way you squint. I can only do 5 minutes of griping? This is tough. Okay, what do I care about? I hate this business where you type the name of a function in the session in order to open the editor. Not only is it a ridiculous amount of extra typing, but sometimes it screws you up. I was about to type some code, and then I have to go back and find a place to type this in, and then the code is active, and all of a sudden things get executed that I didn't expect. Why don't we just do this? In general, I don't like the session log anyway. I like the non-drag down behavior, because I often like to do little experiments on the page. I have maybe an initialization line, and then I'm going to try something, see a number, try it again, see it a number, and I don't want to be 20 inches down when I want to click back on this thing. I want to do it all within sight, up and down. Here's a weird one. I don't know how anybody either handles this or tolerates it. What I did was to sprinkle my code with 1 million calls to a little function that corrects all the dots and commas and low minuses in all the sub-expressions where it wants to be done. Surely some APL standard says that we should cater to non-English speaking countries. No? No? It makes me feel like a great expert that I can remember 16807 and put it down. And, I'm showing APL to a novice, and I say, don't worry, son, you'll get it. I did. But when I don't feel like being supercilious, why not? Or when I'm tired and I can't remember what that number is there any particular reason we shouldn't have something readable? Yes. Okay. And how about this one? I was used to, again, on STSC, that as a cheat sheet, they would tell me what the date is. Now I have to find a little function, and it's going to be different than somebody else's little function, differently named, and it's one more thing to get lodged on my brain. Okay. 2. Okay, well, all right, I had a choice. One was to tell a sort of long story about this case, and the other one was a story that Larry Breed told me about Al Rose. So Al Rose was, as Roy, I guess, mentioned, was one of the folks at IBM when I was there. And he was a little older than me, but not an old fellow by any means. And he was our fix-it guy. He would do everything. He was the scrounger, like in The Great Escape. And so he's the one who put together the portable computer. We had this time-sharing system, and with one suitcase he put a 2741, and the other case he had a modem. And I remember once I carried these things down to the city, maybe to show my sister, and I don't remember why I stopped at a corner and used a payphone to call back to Yorktown Heights with this thing, plugged it in. Maybe I needed to look something up on the computer. So you could do that. So he and John Lawrence, I think was the name, an older fellow, drive to the airport in Al's Skyliner. And first Al pulls these suitcases out of the trunk and hands them and calls someone's a skycap and hands the suitcases to the skycap and said, be careful with those, it's a computer. And then he starts winding down the roof of his car. This fancy thing had these little screws that turn up, and then this mechanism starts doing something, so I'm told. And at this point, the skycap turned to the older fellow and he said, "Mister," he said, "your son's a genius." Okay, that's all we have time for.